discussion of Chapter 4, and the topic is transformed sections. Now, we're going to talk about transformed sections only in terms of reinforced concrete, although your book gives examples of different types of composite materials that you would use a transformed section to analyze. But the reason that I only use reinforced concrete is because it is such an important element of building. And it's really the one element that, the one building structural member, so to speak, that really requires analysis, especially if you go into civil engineering. But the processes that we go through today to transform the section, the reasons, the philosophy, and the execution are all the same for other types of composite materials or composite structures as well. So having said that, let's go over to the document cam. And what we are going to be talking about are transform section, and our focus is going to be reinforced concrete. So when you start working the homework problems, you will rely heavily on sample problem 4.4, which is on pages 266 and 267 of your textbook. All right, so let's talk a little bit about what the purpose is. All right, let's talk about reinforced concrete in specific. First of all, whenever you have a slab of concrete laying down, like this could be in a shop floor, it could be in the bottom of a Quonset hut, any time that you have a concrete slab, there's a problem with concrete. And the problem is that every time that you have a slab like this, especially as a floor, it is most typically loaded only from the top. In other words, if you were in a shop, you may have trucks on top of it. If you're in a Quonset hut, maybe you're laying grain or some other type of commodity on top of it. And what that does is it tends to make the concrete slab bend like this. So in other words, we have some sort of a moment as though we had a C-clamp and we were bending it upward into this sort of configuration. Well, the problem with concrete is concrete is very strong in compression and very weak in tension. So for this reason, it is not a homogeneous, but it is rather a heterogeneous material. So the idea of homogeneous versus heterogeneous always reminds me of the opening line of the novel Anna Karenina, where the author says all happy families are the same, every unhappy family is different in their own particular way. And heterogeneous, that's kind of like homogeneous. Homogeneous materials are all the same. Heterogeneous are all heterogeneous in a particular way. And the heterogeneity of concrete is that it does not behave well in tension at all. So why do we use concrete? Why are we so committed to using concrete?
Because it's cheap.
Yes, it's cheap. And we can pour it into particular shapes. We can create a mold and pour the concrete into the mold so that we can have it take on the shape that we need. And it is also, this is a word, it is ubiquitous, meaning it is everywhere. So if you went to a building site and you wanted to form something out of concrete, there would be concrete available to you to do that particular item. So for all of these, and the other reason is in compression, it's really hard to beat. It's very strong. And it also wears very well. And then, in addition, there are some other properties, which I won't go into. But for example, its expandability, contractibility with stresses and also with temperature are very well defined. So we can always analyze it very, very closely. All right. But we have to compensate for this problem. When we have any material, including concrete, that bends like this, okay? What happens is, as you recall from our previous discussion, that at the neutral axis, sigma is equal to 0. Above the neutral axis, sigma is negative, signaling that we are in compression, but below the neutral axis, sigma is positive or in tension. Yes?
No, just a side question on that.
Sure.
The tension in this and at the midpoint is going to be the same. Isn't it true that the length on it also?
Yes. Oh, very, very true. Yes. When you look at that profile, we talked about this, but I probably didn't ever come out and say it specifically. But if you look at sigma and you put an axis here, what we discussed is that sigma is a linear relationship where it is, in this configuration of bend, the maximum compression is at the top and then it proceeds linearly down to where at the neutral axis, sigma is equal to 0, and then it proceeds to a maximum tension right here. At the same time, if we look at epsilon, which is the strain or the fractional change in length, we will have the most change in length in terms of shortening here, and the most change in length in terms of elongation here. And once again, that is a linear relationship. And at the neutral axis, it's equal to 0. So it's very, very true. Absolutely. All right. So when we realize the way that we solve this problem, that concrete will not accept tension, is we implant, for lack of a better word, rebar or reinforced bars of steel, which is very good in tension, very strong in tension. Into the concrete. Now, where do you think we would put that? Above or below the neutral axis? If what we're trying to do is to get it to bear tension, where is it going to go? I just feel like you guys would know that. Maybe you're afraid to say it. It's going to go below the neutral axis. There's no point in putting it above the neutral axis. Above the neutral axis, the concrete is behaving beautifully. You know, we're all happy, everything's in compression. Oh, I need to show another example of that. But we implant rebar into the concrete below the neutral axis, and therefore the tension is transferred from the concrete to the rebar. Okay? Now, physically, this makes a lot of sense. In terms of our analysis, we can no longer draw the actual geometric slab because what's going on above the neutral axis and below the neutral axis are not homogeneous. Yes?
So we know that concrete works in compression.
Yes.
If you have a flat piece and you press on it,
Yes.
realistically it's got the same amount of force of compression as it does pulling on it. So you want the bars on the bottom to support where it's weaker.
Yes, well, you want it to support, you want it to transfer all of the tension to the rebar. Absolutely. And if you ever look at rebar, let's see if I can find a picture of it since we have, let's find an image of rebar. Let's see. From the PC. Aha, this is beautiful right here. Okay, if you look at this picture of rebar, do you see how it has these little grooves and discontinuities in that? That's so that the concrete will form into it. You don't want the concrete to just be around the rebar. You want it to become integral to the concrete itself. And so the concrete, when you pour it, all fills in these little gaps and grooves and everything. And then you have, here's another good picture. If you'll show it to me. There it is. That's beautiful. This one has spirals on it. They're like big screws. And what you can see is that the concrete would sit down in here, and then it would bond more or less to the spirals on that rebar. So, and that's what you're getting at. That's what you want. You want to have the concrete hold the, it's very funny. This is not a technical description, but basically what you want to do is you want to have that concrete hold the rebar in place so that the rebar will bear all of the tension, because all the concrete is really going to do below the neutral axis is keep the rebar where it's supposed to be. That's all it's going to do. And then the rebar is going to bear all of the tension. All right. So, in other words, in the past, when we drew pictures like these, we knew that the physical geometry of our structural member matched the stress bearing and the change in epsilon diagrams of the structural member. But when we have a heterogeneous material of any type, the stress diagram is not the same as the geometric diagram. So what we have to do is to take our geometric diagram and transform it to a diagram that looks like how the stress is being borne. And so for reinforced concrete, what it looks like is this. We have concrete above the neutral axis, and we have some representation of rebar below the neutral axis, and they are separated by some distance x. So this is like a picture of a prototype of an airplane in a wind tunnel, where the prototype that you put in a wind tunnel really doesn't look like the physical airplane because there's something else going on with the surface roughness and the viscosity of the fluid and so forth. So the transformed picture of the reinforced concrete does not look like the physical picture of the reinforced concrete, but this is what we need to know in terms of our analysis. So I'm going to start by showing you section number 4.4. And I'm going to work a different problem, but you'll see here's a picture of a truly reinforced concrete. The slab is 5.5 inches tall. The rebar pieces are on 6-inch centers, which means that the center of one piece of rebar to the next is 4 inches. And we are bending this upward. You'll see that the moment looks like that. What that means is that this reinforced concrete is a slab, so it extends back this way. We're just looking at a piece of it, and it's being loaded on top, and so the moment is bending it. I'm going to do something, since it's my book, is bending it like this. Okay? That's that little arrow diagram right there. So what we're being told then is that the entire slab is 5.5 inches in height. That distance from the top of the concrete slab to the center of each piece of rebar is 4 inches, which means basically that there's 1.5 inches below the center that's really also not doing us any good. So we have a couple of places where the dimension in this direction, which they're calling x, are just sort of like void spaces. And that's the next part we're going to talk about, is how we draw this physical piece of concrete to look like the transformed section that represents how the stresses are going to be borne. So if we come over here, this is what it looks like. Now we're only analyzing a 12-inch section. In other words, this slab is much greater than 12 inches. But if we're just saying 12 inches, what's going on right there? All right, here's our neutral axis, so here's our concrete, and we're calling that distance x. We know that the distance from the top of the slab to the center of the rebar is 4 inches, so this entire distance is 4 inches. meaning that this distance, although we don't know what x is, the distance from the neutral axis to the rebar, the transformed rebar, is 4 inches minus x. Because 4 minus x plus x equals 4 inches. So you notice once again, that's not the 5.5 inches, the entire height of the slab. It's just from the top of the slab to the center of the rebar, because that's where the main part of the stress is going to be born. All right, so how do we decide what this, we're drawing this piece, so this is a strange thing. This is the area of the rebar times the ratio of the moduli of elasticity, meaning that we're looking at the rebar as being a stretchier version of concrete. So we're saying if we had concrete that behaved like rebar, how much of it would we need in order to bear the tension below the neutral axis? All right, so if you look at this particular problem, I'm going to work one for you next. This is very important that we have one worked, but you can follow through this. You can find the area of the steel, or the area of the rebar. We know that that's pi d squared over 4, and in 12 inches, these are on 6-inch centers, so you're going to get 2 pieces of rebar in 12 inches, which is why it's 12. So you calculate the area of the steel. Then you calculate the ratio of the moduli of elasticity, which, as you recall, the modulus of elasticity for any material is the slope of this line, or in other words, it's how stretchy it is, how much it expands, how much epsilon there is for a given unit of sigma. And so we put that ratio, and this one is 8.06. So then you multiply that ratio of the moduli of elasticity by the actual area of the rebar in that slab width, and you get a transformed area of 4.95 inches squared. All right, so what we do then, the next part we want to do is to locate the neutral axis. And since we have something above the neutral axis and below the neutral axis, but we don't know the dimensions, we have to set up an equation where this is area times the distance between the two centroids, or between the centroid of this and the neutral axis, minus this transformed area times that same the distance from here to here, and we get an x value. So now we know how tall the part of the concrete above the neutral axis is. In other words, how much of that concrete is going to bear compression. And then we can also see that the rest of it is going to be just borne on this transformed area of rebar below the neutral axis. All right, now this is a little bit different. We have to compute the neutral axis. We have to compute the moment of inertia based on the position of the neutral axis. So this 1/3 12 times 1.450 to the third. This is 1/3 base height to the third, which is the moment of inertia of a rectangle. So this is above the neutral axis, about its base. Because the base, see, here's the 1/3 right here, about its base. Because the base of our section is the neutral axis, which is what we are taking the moment of inertia about. The next one, this is the area, the transformed area of the rebar times the distance squared between the location of this transformed area and the neutral axis. So that's the total, 4 inches minus x, 1.4, and we get a moment of inertia in inches to the fourth. Now this is really using the parallel axis theorem, which you don't have to really remember this, but it was introduced in statics. So if you haven't had statics, this may be a new idea, but I'm not going to really delve into it at this point because the geometry of what we're doing is so specific. All right, we're only doing slabs of concrete, so you can use this as a model for your work. You don't have to worry about what it would look like if it was a circle of concrete or some other configuration, because we're only doing rectangular slabs. Okay. So then we are going to find sigma in the concrete, which is going to be compression, mc over I, right? We computed I, moment of inertia. We know c, which is the distance from the neutral axis to the top, and we are given the moment, So we have that. The stress in the steel is the same thing, MC over I, but we need to multiply it by that N value again because we're transforming concrete into rebar. So the sigma in the steel is MC over I times N. There's the N value that I found right here. The moment, which was given in the problem. C, which is the distance from the neutral axis down to the center of our transformed rebar divided by the same I. And so we have this value. So what we find here in this configuration is that sigma in the steel is 1.3 kilopounds per square inch. The sigma in the concrete is, and this would be in compression, right? But the sigma in the steel, which is tension, is 18.52 KSI. Okay? So if you follow this as a model, you'll be able to successfully analyze slabs of reinforced concrete. And this is what I'm calling on you to do in your homework and on the exam. So this example is exactly, it's almost a cookbook, what you need to follow. But what I wanted to do before I worked a problem was give you a model to follow, but also introduce the reason we're doing this. Because if you really think about it, if we did not reinforce the so this is a really great engineering problem. Because what happens here is, without reinforcing the concrete, we have a material that will not suit our purpose. It is not fit for this, it's not fit for the purpose that we need to create with this particular type of material. So what we've done as engineers is we've found a way to make concrete work for us, and then the analysis has to follow. So that is I love that because it's an engineering design method. It's kind of the opposite. It's not the opposite, it's the reverse of the scientific method, where you take a whole bunch of stuff and see what it means. In engineering, you know what you want, and you start with what you can work with, you know, and you work your way down. So it is a little bit, it's a really good engineering analysis problem, as well as teaching us something very important about reinforced concrete in general. All right. So what I'd like to do for the problems, I'm going back into your textbook, and I recall that there are limited numbers of problem with reinforced concrete. So I need to be careful. All right, so there are only a few problems, 47, 48, 49, 50. So let me just write these down for a minute. Just 4.47, 48, 49, 50. 51 and 52, I would not use anything like these because they refer to a different geometry of the concrete. It's actually sort of a T-topped slab, so we're not going to do that. And then 53 and 54 also deal with this type of a configuration. So I'm going to stay very specific to this type of a problem. All right, so what I will do is I'll work one, because I have 20 minutes left, and then I will assign you 2 on your homework, and that's the end of the homework for Chapter 4. Okay. I'm going to do problem 4.49. And then for your homework, I'm going to assign 4.47 and 4.50. Now 4.50 is very, very similar to 4.49. They're both very similar, but if you have 4.49 worked out in your notes, or if you watch it, 450 will follow. It's just, we have a different spacing maybe. Let's see, assume 3 numbers.
I have a question.
Yeah, the spacing on the rebar is different. Yeah.
It's just so our first part of our homework.
Yes.
For today is.
No. Whoa, yeah. Okay, keep going.
So we're gonna do 2 different homeworks on Chapter 4.
Right. See, here's the first problem set. Oh, you can't see that. Sorry. This is on your Moodle page.
Okay.
Submit homework number 5. The first part is 4.1 part B and 4.2 parts A and B. And then after, well, I can just do it right now since where am I? Oh, I would love to edit this, but I'm in the wrong function. All right, so let's go down here. Is my editing on? Okay, so if I come down here to homework 5, I'm just going to fix this right now so that it will all be there for you.
I was a little confused about that, because, and we do have homework due today, right?
No, you had, the homework is not due today. You had homework due Wednesday on chapter 3.
Yeah, I meant.
Right.
Okay.
But yeah, so I said it's due today, but you don't hand it in today. It's all under the same heading of homework number 5. Okay?
Okay.
So when I edit the settings on this, we have the second homework set right here. Would be 4.47 and 4.50. Okay? So now we should be all set. And that is actually due next Wednesday when we have the test. So on Monday, we'll have a review for the exam, no new material presented. But please, if you can have your homework done, I can answer all kinds of questions about it so that you'll be ready for the exam. And we'll also talk about what an exam looks like in here. Okay, so what you're allowed to bring in and so forth. All right, so let's take a look at problem 4.49. We have a slab of concrete that looks like this. The entire slab is 540 millimeters in height, and it's 300 millimeters in width. There are 4 rebars, reinforced. There are 4 steel rebar pieces in here, and the center of those pieces of rebar is located 60 millimeters off of the bottom. I'm sorry, this should be to the center, not to the top. Okay, so we're 60 millimeters from the center to the bottom of the slab. We are told that each piece of rebar is 25 millimeters in diameter. Okay? And so there's our physical geometry of the situation. So the problem reads, the reinforced concrete beam shown is subjected to a positive bending moment, which means it's being bent up this way, right? We're loading it on the top, the slab goes back, into the page like this for some distance. Right? And we've got some hidden, and the bars just extend all the way back like that through the slab. Okay? So I have a positive bending moment. If it was negative, this reinforced concrete, the rebar would do us no good at all. But the magnitude of the moment is 175 kilonewton meters. Okay? Knowing that the modulus of elasticity for the concrete is 25 GPa, gigapascals, and the modulus of elasticity for the steel is 200 GPa. It asks us to find the stress in the steel, and that's of course going to be in tension, and the maximum stress in the concrete, which is going to occur at the top of the slab. Okay? Just like we said, once again, we get back to that little graph, linear, the maximum compression is at the top of the slab. All right, so we can go back and look at problem 4.44, and the first thing that we do is we transform the section. So what we know about our section now is that the concrete below the neutral axis will not bear any stress, so that we're going to have a transformed section of rebar, and the area of that is going to be n, the ratio of those 2 variables times the actual area of the rebar. So this distance from here to here, we're told, is 300 millimeters, and we call this distance x. We also know that the total distance, this distance is from the top of the concrete to the center, so that's 540 minus the distance to the bottom, which is 60 or 480 millimeters. So we then know that this distance is 480 minus x. So we have drawn our transform section at that point. The next thing that we need to do is to find the area of the steel. We have 4 bars, and each bar, because it's circular, has a cross-sectional area of pi d squared, which is 25 millimeters, over 4. Make sure I've got everything squared correctly. Yep. All right, well, these will just cancel. So the area of the steel is, and I'm going to keep it in millimeters squared, kind of going off my own project here. So if I multiply that, if I square that, I get 625 multiplied by pi. I get 1963.5 millimeters squared. Now the next thing I need to do is to compute n, or the ratio of my moduli of elasticity. So that's 200 over 25, which is 8 even. Okay, so then I compute NAS, which is equal to 8 times 1963.5 millimeters squared, which is 15,708 millimeters squared. All right. Now the next, so this is the first thing I need to do. Well, I guess this is really the first thing I need to do. I need to draw this transformed section. 2 is to compute the transformed area of my concrete, of my rebar. And the third is to locate the neutral axis, which means basically solve for x. All right. So what we can say is that about the neutral axis, we know that, and this is sort of something we haven't really introduced, but if we take the area times the distance from the centroid of this area, which is halfway up, x over 2, that about the neutral axis, the summation of these, which are called Q, you may recall first moment, you may recall from statics, is equal to 0. So I find my Q, which is YdA above minus YdA below, equals 0. That locates the neutral axis. So above we have the area, which is 300 times x times the distance, y, which is x over 2. And then below the neutral axis, we have our transformed area, which is 15,708 times the distance from here to here squared, which is 480 minus x, and that quantity is squared, and this equals 0. Now the one thing that you may see about this, it's going to break down into a quadratic equation, but we'll go ahead and work it out. Here we have 300 divided by 2 times x squared, so that's 150 x squared. Here, I cannot do this number in my head, so I'll go ahead, 15,708. Wait a second. I guess I have to break this up, don't I, before I go ahead and do that. So I have to do 480 minus x times 480 minus x, okay, in order to find that number. So we go, let me go ahead and clear this. 480 times 480 is, let's see, I'm going to go minus 15,708 times 230,400. That's first, then I have to do last, plus x squared, and then in the middle I have 2 times 480, which is 960, shouldn't have done that, minus 960x, okay, and all that added together equals 0, So on 150 x squared, now I need to distribute that number through 160, because I have that one on my calculator, times 15,708 equals, negative times negative is a positive, so this is plus 150,79680x. And then right here, I'm going to have minus 15708x squared. It's minus equals 0. And then I have 15708 times 230400. And that value is 3619123,200. Okay, so this is my constant. So what I'm going to have over here, I'm going to rearrange this so I can write it as a quadratic equation. So we have minus 3619123,200. It's this number. Then I have two numbers in x squared. That would be negative, I have to clear this, 15,708 minus 150, and that's going to be minus 15558 x squared, and then my term in the middle is plus 150,79680x. And I'm really wishing at this point that I would have converted into meters instead of millimeters, because my numbers would be quite a bit smaller. All right, now what I'm going to do, because I'm going to run out of time getting into the math on this, I'm going to go ahead and just show you how I'm going to set it up, and then I will finish the problem on another screencast that I'll do in my office so that you don't have to watch for it. But to solve for the roots of a quadratic equation, the answer is negative b plus or minus square root of b squared minus 4 times a times c all over 2 times a. So in other words, my a value here would be this, my b value would be this, and my c would be this. All right? So when I find that, I'm going to solve for x, and that x, if we go back to our original transform section, is the distance from the top of the slab to the neutral axis. So I can find this value, I can also find this value, and then I'm ready to proceed with the end of the analysis where I find my moment of inertia and the maximum stress in the concrete and in the steel. Okay? So at this point, I'm going to turn you guys loose, and I'm going to just work this out on a different little screencast, which I'll have posted up later today. All right, and then you'll have that as an example to do your 2 homework problems. So on Monday, I would like you to come in with lots of questions for me, and we'll go over this. We'll go over questions not only about this homework, but also about how tests are given in this class and what it's going to look like, and then and what you can bring in with you and all those other questions. And then on Wednesday, we'll take our midterm exam and wrap it up for the first part of this class. All right? Do you guys have any questions for me right now? All right. Well, have a wonderful morning, and the ancillary lecture will be posted today. Have a great day.